when it's 15 past. And then please also, if you could accept the recording, so then we get also your video to the recording of the presentation. Okay, but so yes, good morning everyone, and welcome again to the Machine Learning Coffee Seminar. And then today we will have Aki Vehtari from Aalto University, and he will be talking about on Bayesian workflow. So you are again welcome to write your questions to the chat, but this time we will most likely ask them only after the presentation. But please, the floor is yours, Aki.
Okay, thank you. Good morning, everyone. So this talk, it's partially based on this preprint Bayesian workflow with Gelman, Simpson, Margosian, Carpenter, Yao, Kennedy, Capri, Bergner, Modrak, and of course there are also others who have influenced our work. Actually, 1 year ago, like a couple campus weeks ago, I gave also talk in this machine learning coffee seminar, and it was this FCHI Agile Probabilistic AI talk, and that talk also had small mention about the Bayesian workflow. I had in this hand-drawn figure, and now then last autumn we had then this archived this Bayesian workflow paper where we have also this workflow figure where you can see the numbers referring to sections. And this is so long paper that I'm not able to then go through in this talk completely. Even I can't get it to fit this one figure in one slide. Of course, I can make it smaller, but then everything, the fonts get so small that you can't see, and there's too much to go. But I'll discuss some things I want to develop more on this Bayesian workflow, and some things that I want to kind of emphasize that what kind of thinking in these workflows overall are useful. So I will say a few words about how workflow frameworks improve efficiency, reliability, reproducibility, but then I focus more on this iterative process part, that workflows have iterative parts, and which are then useful for learning, and also I take a connection to software development. I'll talk about practical workflows, so these workflows can't be really rigid, so we can think also of this as engineering. And then these practical workflows, including the iterative process, have then received kind of criticism, and then I discuss that, and then a little bit in the end about connecting these to software-assisted workflows. Workflow term itself is relatively old. So the first mention is at least in 1921 in Railway Engineering Journal, and of course building railways you want to also be efficient and kind of have some kind of guidelines, standardize the flow of work, how to make it more efficient. Looking at the Google Books Ngram Viewer, it seems beginning of 1990s started to get more popular, and we are already past the peak hype. So a bit late of starting using this term. And I did try different like data analysis, Bayesian, statistics, workflow, and so on. And there's only like 2 hits in all different combinations I could came up. So really we are late in using this term. But then they are actually used in data science, so in bioinformatics, and then also with the term scientific workflow. There are these software systems built to make these kind of more like pipelines. So we have here some source of the data, and then we're doing integration, pre-processing, we have here modeling, dividing to training set and test set, validation storage. And the software makes it so that you can have these different models there, and then you can easily repeat, when you get new data, you can repeat this process again and again. And so you get this reproducibility and efficiency. What I think then is missing here is that it's not actually telling how this modeling part is then constructed. I mean, in a way that, like when I talk about Bayesian workflow, it could be also other data science workflow, discussing specifically how you would go up making models. The bioinformatics was the first where there was a lot of data coming and they needed these reproducible pipelines, and they made software, but then other also noticed that they can be useful. And here's, for example, then from physics, and again, similar kind of that having models, and also note that there's can be different sub workflows, experiment workflow, analysis workflow, modeling workflow. Still here, the modeling workflow is also, it's just one path going and then going to the end where you get then the nice end result. So overall, although the workflow in Bayesian modeling or in data science general is new word, it's actually quite old to have in different engineering and these kind of guidelines, and they improve them this efficiency, reliability, reproducibility. The Bayesian workflow term, it seems Jim Savage, 2016 in his blog post, was the first one to use this term. I do disagree with that there would be just one Bayesian workflow. So there are so many different cases how what kind of models to build and in which kind of cases and what purposes and so on, that there are actually many Bayesian workflows. And then this our paper with Vehtari, Simpson, Betancourt, and Kelman seems to be the first article using Bayesian workflow in article. But I'll go back in time before the workflow term itself was used. George B. Box is very famous Bayesian statistician, and in 1955 with Youle, he had this paper with catchy title, The Exploration and Exploitation of Response Surfaces, an example of the link between the fitted surface and the basic mechanism of the system. And it had this nice figure Box has used also then later, where there's the kind of the, instead of iterative, it's also has this arrow in time and increase in knowledge, but in a way that you have a model, you get more data, you update your model, you get more data. And Box was working specifically in design of experiments, where the experiments are also then, like in industrial process, you make new measurements also, and then you update your theory or model and you learn more. This Box's 1976 paper, Science and Statistics, is more famous, but it has the same, the idea of the advancement of learning and iteration between theory and practice. And here there's the practice, data, facts, and then you can update your hypothesis, model, conjecture, theory, idea, and then you can increase your knowledge by getting more data or learning. Based on using your model, you can learn more, and so on. And then it was also then illustrated where you actually have this feedback loop going around, and where when we learn more, we update our model. So this iterative feedback loop. Also more simpler figure in the same model. In box 1987 talk available in YouTube, additional steps, identification, fitting, diagnostic, checking. In Bayesian data analysis book 1995, there's also 3 steps: setting up, conditioning on observed data, evaluating, and in response, repeat the 3 steps. So again, description of this iterative workflow. So really we haven't done anything in that way really new in the workflow or proposing iterative process. But still, it's been common also that this Bayesian workflow, and if you look at the other data science workflows, they tend to have still really often this, that there's one direction, and then you might have here sometimes then going back here, which is quite simple if you compare them to what we now present, and this is not even the most complete, or in a way that if you look at the paper, you could add even more boxes there and even more arrows, more loops, and you can see there are these different possible paths to go around, so that it's not just one loop, there's many different ways to loop around. And there's even give up. So sometimes it is possible that the specific box discussing addressing computational issues, there can be that you give up on certain model because you can't make computation for that, and you go to modify the model. So you can see that there are many different possible workflows. And I also like to use term sub workflows. In addition that we have different loops going there, it's also that if we look at something like simulation-based calibration here, that simulation-based calibration itself has its own workflow and loop. And so we have also sub workflows inside in these different boxes. But then again, in this talk, I want to emphasize now this iterative process as a learning process, and then as a kind of the engineering process. So even if we would be able to create our models easily, and then we would be able to make perfect inference, it's still likely that we don't want to make right away very complex model. In some cases, we might know beforehand, okay, that based on previous experiments, something very complex is applicable right away. But when we are examining new phenomenon for us, we can start from a simple, because incremental learning reduces cognitive load. This is how we also teach children and also adults in universities, that in the courses, we first teach something simple, and then we start to gradually build on top of that more complex things. And in the same way, when you are studying new phenomena, making a modeling for that, you can use this approach that you first make a simple hypothesis, simple model, and you learn something from data. And you can then use that model to learn more about the data, update the model, learn more about the data, and so on. And we can also then think these models as experiments, so that we can think that even if we have just that one data, when we have a new model and then fit that model to the data and look what we can learn using that model for that specific data, this is experiment also. And then based on what we learned using some model for the data, when we update the model, we are creating new experiments. So then when we are modeling a new phenomenon, we can think this as active learning and sequential design of experiments, sequential design of new models. And then this is something that we should think about also when we write about workflows or make the software which can assist with the workflow, that we need to think about it. It's not just one static pipeline. It has this iterative process often. There are, of course, also cases where we can just, oh, this is so similar to the previous case I've had, I'll just copy that pipeline and that's enough for me. I don't want to learn anything new from this data. There's also a clear connection to software development processes, especially when we are doing the modeling, the new models, we are writing them actually as a code. In probabilistic programming, we are writing with these probabilistic programming languages, we are specifically writing the model. So it's clearly writing code. But then also on top of that, we can think about overall in a bigger framework, what we are aiming. One popular kind of case for also many more later refined approaches is this poems spiral process, where the idea is that we can make software faster by starting with some prototype and then doing reviews, determine objective alternatives, constraints, evaluate, identify, resolve risks, and then we come with some other prototype, and then with some other prototype. So going in loop, so iterative process. And this is also brings now this kind of software engineering part, that it's also that with these first prototypes, we can do less testing. And then when we have more refined prototypes, we do more detailed testing. And this is also applicable then in this model building, that we often can start with some very simple model and quick inference to learn something. And then we can, based on that, build new prototypes. But also in the end, when we have some interesting model, we need to do more detailed testing in the end to verify that everything we did is well made in statistical sense. The differences are that usually the single models are smaller than software projects. It's also that the end result may also be series of models, so that if we think about this, we had the advancement in knowledge, and then we had the data models. And then if we go advance in, like in the box diagram, it is also possible that we want to actually report these different models. because it's also then that when we are, even if the first it was that we use the iterative learning process that we learn ourselves, but when we are communicating the results, it can be again easier that we report that, okay, with the simpler model, we can see from the data these things. And then if we take this kind of component, how the model changes and how much we can learn from the updated part, and how we, again, one change changes the situation. This has been used, for example, in these COVID modelings also, that showing first simpler model and then showing that if we add more components to the models, how our estimates of like this R value changes, and it then helps to see the kind of the how big effect the additional components have. And then in that case, we are actually also kind of not just making a release of the most complex model, but also these. And of course, we might have had actually the iterative model building inside in these. We were doing small refinements to get them good and working and computationally efficient. So they are these different layers all the time. That Boehm's spiral process had these prototypes, and now sometimes these the Bayesian workflow or data science workflow examples, they seem kind of rigid in that way that they are saying that you have to do these steps every time. And then I'm saying that in the initial phase, when we are doing these prototypes, we don't need to follow all the rules strictly or make as strict diagnostics and so on, so that we can do these kind of prototyping and initial experiments. It's the same thing as in overall in engineering. When engineers build also physical things, they first make quick prototypes that it's something that's just proof of concept. And in the same way, we can when we show some example workflow, like we had the figure in our paper, which has many of these boxes. Actually, in the early phase, you can skip some of the boxes, and then just in the later phases, come back and check that everything is rigor. Another reason that often do iterative model building is this cost and benefit of model building, that if this is the how fancy model we have, and then this is the benefit of the model, it's likely that these are something like this. Of course, because of the computational issues, it can be also that for too fancy model, actually the benefit drops, that we don't even get good predictions. But assuming that we can do this inference, well, it can be something like that. So at some point, there just isn't any more useful information in the data that we could learn more fancy model. It is possible that the true phenomenon is more complex. Like we know that we need relativity theory for satellites, like GPS satellites, but we don't need relativity theory usually down Earth, even if relativity theory still holds also here. It's just that we don't have that accuracy. And even for GPS satellites, it wasn't kind of trivial to get that accuracy that relativity matters and we get the GPS working accurately. But here, since this curve is like this, it's possible then that there are these different types of models, and then instead of right away going here, you might want to be happy with this model, and then one way to find this model is that you start with this and then go forward, and then it's possible then that the time you needed to make these three models is much less than if you would have started with the most complex model. And so if we add also the so there's fancy benefits, and then if there's, for example, time cost making some model, it might be like this. So another reason why smaller models might be helpful. Part of the workflow ideas is, of course, then we try to also then make these curves so that we can build also more complex models more efficiently. We try also make it so that more people would be able more easily build these more fancy models and get bigger benefits. So I described different reasons for why we advocate this iterative model building. And then this is usually then criticize these kind of ideas is that, oh, now you are using data more than once because you made one model, you fitted that to the data, you learned something, and then you modify your model, and then you fit it again. So you are using the data more than once, and this is also called sometimes double dipping. And then that using data more than once is then violating kind of the probability theory and Bayes theory. It's also kind of criticized that kind of the inference after model selection, if you have two models and you select one, that the usual approaches for inference are then biased. But then the good thing is that we also know why this iterative model building can, however, be safe. One is that we know that if we have many models, then the correct true way to handle many models would be integrate over the model space and average over all. But if in that integration, some of the models would get weight 0, they can be dropped out. And in the same way, in iterative model building, even if we have many models, it is possible that we can just use the final model if the improvement from one model to next is so big that if we would also integrate over this kind of the workflow process, the other models would have negligible weight there anyway. We have also, we know there's a proper decision theoretical approach for making inference after model selection. So that's also covered. It adds a bit more complication, but it's doable. Missing perfect calibration is another problem. If we don't have too much of the using data more than once problem, if it's just slightly making our inference miscalibrated, that's not a problem because perfect calibration happens only in simulated toy problems. As soon as we are doing analysis of real phenomenon, our models are not perfect anyway. And if we don't have perfect model, then we don't have perfect calibration. And then additional small bias doesn't matter. But of course, how we know then whether we have negligible additional bias, it's diagnostics. So we have already some diagnostics for this, and we are developing more so that we can see when this kind of building many models is safe and when we need to be more careful. And then there are additional videos discussing some of these aspects. And then how we can make these workflows much better. It's just writing like this paper with more than 80 pages or writing a book. It's not enough. It's not easy to digest all that information and then apply it in your work. It's easier if computer is helping you. And we have already a lot of things that we can consider that are kind of computer-assisted workflow parts. We have code generation and libraries like in Stan, there's a BRMS and RStan ARM, and for PyMC3 there's a Bambi, and which have much simpler syntax for writing many simpler models. But you save a lot of time making quite fancy models, and there's less danger that you would have bugs in your model code. And then, of course, like in software development, usually, if there's a library that you can use, it's better to use that well-tested library than writing your own code, so code-ready use. These computational graphs, as I showed in the beginning, this scientific workflow software discussion, these pipeline graphs, and there's also like for in data science in R, there's this targets package, which can also make these certain things that you want to rerun again and again, and reproducibility, so that like if you change something in your data pre-processing, everything else in your data analysis pipeline, modeling pipeline would stay. They are still in the early phase that they are not yet well suited for this iterative processing or this incremental learning part, but I guess they will develop. And then, of course, these diagnostics that are sometimes called automatically, or then that you can call them yourself, different packages, which then tell that what you should do as a next step. And of course, then combining this all is a lot of work. And we want to go towards this more robust inference and diagnostics that have their own diagnostics, automated sub-workflows, and allowing shortcuts, so that from the user perspective, they can skip some things that are usually recommended, but they can skip them, especially in the early phase. But we would have automated diagnostic telling whether that shortcut is the safe choice, and then telling that, oh, actually, now it seems that you have to be more careful in this part. And then this interplay between software diagnostics and documentation is then a very complex thing. Okay, that's it. And here's just a reminder, the topics I went through. Now I'm happy to answer questions.
So thank you for the very interesting presentation. Do we have questions from the audience now? Well, while the others are still considering, so I guess you are quite well now following the workflow in your own research group in the research. So what kind of processes have you developed to follow this, or do you very strictly do that, or is that always on the case basis?
it's all on case basis, and it's also that right now we are not doing much applied work, and then our ideas on these, how to do these things, have developed. So currently it's more like that, experimenting with these ideas in different smaller case studies. And I know other people that are then who are doing applied work that are following these workflow guidelines we have, and but it really is the kind of what is missing, that there would be more software assistance for this. So then that's why it also makes it that it's not that common that it would be like easy to get description what was their workflow exactly, that they don't necessarily share everything. And it's also kind of what to share, because if we think about overall scientific communication, it's not typical that you would report every step you made in the initial phase and every kind of the problems you had. We are making also that kind of case studies now, illustrating specifically that like what if there's actual error in your model code, how you can then diagnose it. But that's not something that people commonly report. So we need to specifically make these kind of examples where we, so that, oops, now based on diagnostics, there was a mistake or error, and this is how we found out about that problem, and this is how then we would proceed fixing it.
Okay, great, thank you. And then there's a question from Anna. Would you like to ask that by yourself, or do you want me to read the question?
Yeah, I just wanted to ask, so you say that there is some optimal model, and we know it from common sense. So if it's too much computation, it's bad, and if it's too simple, it's bad. But what is the theory behind this optimal model?
Oh, in that I referred that sometimes you might be working on very similar data sets again and again. So so this has been also kind of the related question from other direction has been before that, why should I start always with the simplest model if I already know that this more complex model is useful? So in some cases, some people might know that, okay, I'm analyzing very similar data sets again and again, and then I know that this model is quite good. And so it wasn't about optimal in theoretical sense, it was kind of optimal in practical sense.
Okay, thank you. And then Sami.
Would you like me to ask? Yeah, I can.
Please, yeah.
Now the approach brings to mind that in bioinformatics, that was actually for the empirical experiments where the new high throughput technologies came to picture, and it was a wild west, and people reported what they wanted and nobody was able to reproduce results. Now, that reminds me, I have never thought about modeling in the same sense that modeling actually is in that stage. It's very difficult to reproduce what others have done. Mm-hmm. So what is, Aki, your take? Should we be more orthodox and give the acceptable standards, even with the risk that then modeling will become much more boring and will advance more slowly? So pluses and minuses.
Yeah, so I think that currently the minimal standards would be that publish the code, the model code, and then also reporting these inference diagnostics. For example, if using Markov chain Monte Carlo, then reporting convergence diagnostics, possible model checking diagnostics, but then that seems to be currently the minimal standard, and there could be more. There have been a lot of discussion of that reporting these different model choices, that kind of that if you started from the simple, and then if there's two different options where the brands, that you should report also that why did you choose certain brands in your choices, that okay, I decided to go into towards this kind of models, and then again it might be brands, and then some people are also then reporting these multiverse results, showing that actually all the possible models they could have come up with in these different branches. And then of course I think that can be also sometimes useful, and I would in kind of especially if the diagnostics say that okay, these decisions are in that way uncertain, that this branch might be also likely good model or likely good explanation, then we should report this. Some of the kind of the more strict, that like some people have been recommending that you should always do the simulation-based calibration of your inference algorithm, which is very time-consuming. So there are also these possibilities that if we would include too many things that would be part of the minimal standards, that there's too much work could also drive people away or just slow down progress. I don't know if there's good just a minimal standard, but at least there could be kind of a checklist that check out as many of these as possible type of thing. Maybe there could be then also that at least these some few as a minimal.
Yeah, thanks. And maybe Nature and Science would have a longer checklist, and then some more Wild West type of journals then would have a shorter checklist.
Yeah, and then since the goal is anyway that many of these things can be done more automated or computer assisted, there should be more and more of these things from the checklist that could be required. And of course, like I would say that more it is about like that these modeling results might be used for decisions where there are human lives. So like COVID models or models for predicting what kind of treatment to give. In those cases, I would do very, very careful work and go through many of these checklist items.
Okay, thank you. Still time for one question, I guess. But there doesn't seem to be any. So thank you again for the interesting presentation, Aki, and everyone for attending and the good questions. So we will meet again on next Monday. Thank you and bye-bye.